Okay, I just started the recording. I just realized I'd forgotten to click start. It's going now. So for those who are just joining us, we're going through this horrifically long homework assignment, and I apologize to you for the length of that. It will not happen again. And if it does, you can email me and tell me that I need to fix it. Okay, so anyway, we're on number 27, and we only did number 14. 14, I can go back to that in just a minute. But so number 27, finding A is relatively easy. It's just an algebraic expression. And then the second part, finding the letter B, is also using algebra. So to do that, I'm going to do this. F of 3, since this 3, f of 3 has to be 24. So let's plug f of 3 into this expression. That's going to be A times B to the third. But I already know what A is. A is 3, so that's going to be 3 times b to the third. So 3 times b to the third should equal 24, which means b to the third is equal to 8. And hopefully we know what b is now, but if not, you can always use your calculator and do the cube root of 8, which is 2. So b should be 2. So the final answer is b equals 2, a equals 3. All right, so I'm just going to, for the people watching from home, I just want to switch back to the other one. Okay, so it's flickering even with this. Okay, let's see, go back to, here it is. So if you were confused about number 14, there are the answers. Basically, algebraic just means things that aren't exponential or sines or cosines or logarithms. So. All right, anything else from this that we need to look at? And we can take our time, like I said, and if you need more time, I haven't looked, I probably will. I've already pushed the due date back to tonight, only so that I could actually view it in front of you, because it kicked me out at 8 o'clock this morning. But I could push it back even further, because this is basically just a review of your pre-calculus, and it may have been a while since your pre-calculus. Elena, what's going on?
Could you cover question 30?
Absolutely. So many questions. Yeah. Here we are. So, oh yeah, this is so good, because it reminds us of our rules of logarithms. Okay, just a minute. Let's see. Okay, so here we are. Back to this. Paste this in here. Give me a sec. All right, that looks good so far, but if it starts being bad, we will fix it. So rules of logarithms, let me just scroll down a bit. We'll put some rules of logarithms here, just like the rules of exponents. Let's do the rules of exponents first. So e, or any number, let's get rid of that e, because that could be anything. A to the n to the m is a to the nm. So these are what I mean by the rules of exponents, is things like this. If you have a to the n times a to the m, you get a to the n plus m. Okay, that looks good too. And then a to the n over a to the m is a to the n minus m. So hopefully you recognize those as being the rules of exponents. The rules of logarithms are pretty much the same, only they've been sort of turned upside down. So let's see, logarithms. If you have the log base b of xy, you get the log base b of x plus the log base b of y. And that is basically the same as the sum rule for the exponential. The exponential rule for the sums, it's basically related to that, because logarithms are exponents. They're just the exponent for this particular base and that number. The other ones are these, the log base b of x over y. If you have a fraction, you just take the difference of the logarithms. And then if you have the log base b of x to the n, you just take that exponent out front of x, sorry. Okay, so those are our rules of logarithms. They're related to the rules of exponents, and the only reason I put the exponents up first is because those we're familiar with, these not so much. So let's go back and see if we can apply these to this. First of all, you see that you have a fraction there. I deal with that first, and so let's see, this will be equal to the log of, and I wonder if this is intended to be the natural log or the common log. Well, it doesn't matter in this context. So I'll have to figure out if this book, some books, when you see this without any subscript, it means the common log, the log base 10. And if you, that's probably the way our book does it. And then this is natural log. I'm going to guess that that's the way it is. So this is probably common log. Doesn't matter. It's just a log. So we have the log of the numerator minus the log of the denominator. So do it steps, one step at a time. Then we're going to take that and separate the stuff, this first thing, the log of x to the 5th plus the log of y squared minus the log of z to the 13th. So notice I'm just using those rules of logarithms, and then the final rule of logarithms is I can take this 5, since it's an exponent, move it out front, and it will become this a here. So that'll be a equals 5. This 2 gets moved out front, so I won't actually write it, but hopefully you can imagine what it would look like. And then this 13 gets moved out front, but notice that it's negative, so that'll be negative 13. I'll write it, 5 log x plus 2 log y minus 13 log z. So it's just useful to be able to do these manipulations. Hopefully this is just jogging your memory of something, oh yeah, we did that 4 years ago. Some of you might have been 4 years ago. I know you're advanced students. You had Algebra 2 back in middle school probably. And so if that's the case, that's fine. And just that's why I wanted to go through this. But I probably should have given you more time to complete this because there's way too many problems. So I apologize. That's why I have homework woes, and there is no quiz today. Anything else that we can do that we need to do? And by the way, if you're watching from home and you're thinking, wait a minute, I need you help with number 31, you can always email me, and I'll do my best. Oh yeah, Thomas? Interesting, yeah. So these hyperbolic functions, just trying to think, will they pop up? They don't, I don't usually deal with those until later. But yeah, you're right, the functions, you can get them on your calculator. If you don't know where to find them, you would go to the catalog, and then if you have a Texas Instruments calculator, and you can plug those in. But yeah, those are related to the exponential function. The hyperbolic sign is e to the x minus e to the negative x over 2. Sorry, I had to make sure. It's the average of two exponentials. And same with the hyperbolic cosine. Hyperbolic cosecant is the reciprocal of the hyperbolic sine, and the hyperbolic secant is the reciprocal of the hyperbolic cosine. So I guess to get back to Thomas's original question, you'll need to know them at some point maybe, but no, not in the near future. So if that makes you feel better, you can ignore those. So yeah, this is one of those that I should have properly previewed this, scrolled to the bottom, made sure I cut out any of the ones that didn't pertain to what I cared about. Right, anything else that we can do? So once again, I sincerely apologize, seriously. I'm getting used to this new system. you're getting used to it. This is the first semester I've used this Lumen, and so there's a little bit of a learning curve for me. So, and I know that you're suffering because of my errors, so I apologize for that. But hopefully this will help us to not suffer in the future. For example, the homework preview, hopefully you'll be happy with what we do for the homework preview. It'll be reasonable. So let's go ahead and move on then, if you don't mind. Let's see, where's my stuff? Why is it not showing up here? Hold on a sec. I don't know why it's not showing up. I can always do it on here. Thought it was supposed to automatically update. Here we go. We'll start with this then, and then I will deal with it. Okay, so anyway, going back to trig just for a sec, I promise. So like I said, I've already apologized for that terrible trig homework set, and I will make sure that everyone has a good grade in here, that won't affect your grade. But what I care about is just things like this. Can you deal with the function y equals sine of x? It's okay if you're like, yeah, it's a function. You could think of it in the same class as e to the x. You know e to the x is a function, but you might be thinking of it as it's an abstract function. You don't know what it means or what it does. It's okay. Just be able to deal with that as a function, as well as the cosine and the tangent. Make sure you just be aware that those are functions. They do something like this. They go up and down. SOHCAHTOA, that'll be useful for application problems. So do you know the SOHCAHTOA thing? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. That's it. That's all I really care about in terms of the trig. I don't care about identities. There are a few that I might bring in just momentarily, but I don't care that much about the identities. It's not going to make or break the what's whether you can do calculus. So when will you use it? You'll use it when you're setting up application problems, mainly. So that's the main reason is, so we'll deal with the calculus of those functions, and we will also use it for certain applications, but they'll be basic applications. So don't worry, I'll help you through this. And I've learned another important lesson is that I should not hammer the trig at the beginning because I don't want people to feel too discouraged. Okay, let's move on though and remind you of this watermelon problem. So we're still in the pre-calculus, or sort of the lead up to calculuses today. We're going to talk a little bit about the basic language that we're going to use, limits, secants, areas, tangent lines. So I guess I should have put that on the list. So these are sort of the basic things. Sorry, this is going to bother me. Just a minute. I want to just see why this is not updated. This autosave is on. Where is this? Save a copy. Where is this going? It's on OneDrive. I mean, the whole point of having this iPad was so that I could write on it. Just a minute. Where's my OneDrive? Did OneDrive go away? Oh, there it is. Give me a sec here. There it is. It's right there. I don't know why it didn't show up in my, okay. Just a sec. Can I just open this? Whatever. Okay, I'll do it in Notability. Sorry. Sometimes I think the technology is not worth it. Okay, phew. There we go. Finally got it. Preview of calculus. So this won't be quite as exciting because it won't build like the other one did, but That's all right. I can write on it now. Okay, so back to trig. We already talked about that. The watermelon problem. Oh no. Why didn't it port the... Sorry, I'm on the struggle bus today. Oh, now it's in my... Okay. There, that's better. Sorry, I don't know what just happened there. I don't know why it didn't show up the first time and then it did the second time. So, remind you of the watermelon problem. We're climbing up to the top of the chapel steeple, or better yet, up Raston Tower, because maybe if you have not been there yet, you should go over to Foundation Park, climb up the tower there. I don't know if it's open in the winter, but it's fun. You can see Walmart from the top of the tower. It's really cool if you're not scared of heights. But Raston Tower is approximately the same height as the chapel steeple, so as for comparison purposes, so we could imagine that as well. So we're going to drop the watermelon off the top of a big, tall thing, and what we want to do is we want to compute how fast this watermelon is going when it hits the ground. And if you remember, what we did do is we figured out the average speed. So we did the average between 2 points. And we kept making those points closer and closer together. So we did the average speed for the last second, and I believe it was 80 feet per second. Was that right? So if you did it from 1 second, or well, it takes 3 seconds for it to hit the ground. So if you do it from 2 to 3, you get an average speed of 80. And then if you do it from 2.5 to 3, you get an average speed that's a little bit more, and so forth. And so what we're going to do is we're going to do the average speed. We're going to do, in calculus, we'll call this a limit. So a limit is what happens to the average speed when the points get really close together. Okay, so here's what I mean by the points, is we have, here's the watermelon at t equals 2, and then at t equals 3, that's when the watermelon is exploding on the ground. So those 2 points are pretty far apart. If instead of going from t equals 2, we did t equals 2.5, we would get a little bit better approximation for the actual speed of the watermelon when it hits the ground. What did we do? We did 2.99. Did we get that close? Yeah, so that, the watermelon, if my memory serves me correct, at t equals 2.99, the watermelon was a little bit under a foot above the ground. And so when we did the division, it was like 95.9 feet per second. So that was even better. And so a limit is what happens as you get closer and closer to the ground. Now, let's actually do this. So this is called a limit. So what I'm going to do is I'm going to actually write down what the speed function is. So the speed of the watermelon is going to be it's a divided difference. So we have, let's see, we'll call it 3 minus x. That's how many seconds are going to elapse between the, like, t equals 2 and t equals 3. So, 3 minus t. I should use a t here, shouldn't I? So we'll use a t. And then on the top, I'm going to do the height at t minus 0. So the form I'm using is a little bit wonky, but it'll work for this purposes of this. So basically, I figure out how high the watermelon is above the ground, and then divide that by how much time there is left in its travel. Distance over time is speed, right? So let's do this. That's going to be 144 minus t squared all over 3. Oops, what just happened there? 3 minus t. Okay, so what I'd like you to do is plug in these different values for t. Now, we already did a couple of them. So just to remind you, when you plug 2 into this, we got 80, I believe. We can double check though. 144 minus 2 squared is 140 divided by 3 minus, wait a minute, why is that not working out? Oh, I forgot an important part of this, didn't I? Someone should have yelled at me. It's 16t squared. I was so excited about the denominator, I forgot my 16. There we go. Okay, 144 minus 16 times 4, which is 64. Sure enough, yes, it's 80 over 1. And we also did 2.99, but I don't remember the number that we got for 2.99, so I'm going to do it again. So for 2.99, I would do 144 minus 16 times 2.99 squared all over 3 minus 2.99. And if you'll allow me, I will pull out my calculator and do this because this I cannot do in my head. And I got 95.84. So does everyone understand what I'm asking you to do? Go ahead and see if you can fill in the rest of this table, and then we'll talk about how this relates to limits. So I'll give you a minute or two, a couple of minutes, while I get my randomizer app. Let's do it. Randomize. All right, Bryce, do you know what's happening, what we're doing?
I sure do.
Oh, good, good. You know, that's, I just want to make sure. Not that I just, but if anyone feels like that they don't understand, then if I call on you, you can just say, I don't get it. Bryce knows what's going on. Did you do 2.5?
I did do 2.5.
All right, what'd you get?
I got 88.
88. And I'm guessing that all you did was you changed this to 2.5 and this to 2.5?
I sure did.
All right, it's beautiful. Excellent. You're not here. You're not here. Kelsey's here. Kelsey, how are you doing? Do you understand what we're doing? You can do it? Can you do 2.9?
I can, yeah. I just calculated 2.5.
Okay, take your time. And while she's doing 2.9, I'll put you on notice, Ethan, that you get to do 2.999. So if you haven't done it already, make sure you punch it in.
That's like your graphic calculator.
Oh, nice. So you just have the function and you just keep. What did you get for 2.999?
95.94.
95.94. Okay. Yeah, don't panic.
94.4.
Okay, interesting. 94.4. So the closer we get to the ground, the closer the average speed is going to be to the actual speed. And so as we get closer to the ground, does anyone have a guess as to what they think the actual speed is when you hit the ground? Yeah, what do you think, Elena?
I think it's like forever converging, but never quite reaching 96.
Yeah.
I don't know the technical term.
That's the term would be, well, I guess you could call it an asymptote, but it would be a limit. That's what a limit is you're always getting close, never getting there. So very nice. So that is a limit. The limit, you could guess But we'll do this for real on Friday so that there's a way to figure out that this gets to 96. So notice that you have like at 2, the speed is 80. That's okay. It's like that's an estimate. And then you get better and better and better, and you get closer and closer to the truth. And so you can sort of extrapolate and say, well, it looks to me like the truth is going to be about 96. Sometimes you can do that. You can just eyeball it and say, hey, looks like it's going to be about 96. So this here is a limit. Where is the function going when you get closer and closer to the ground? By the way, if you're curious, 96 feet per second is about 65 miles an hour. So that watermelon's really moving when it hits the ground. Now, I know some of you are going to be like, oh, wait a minute, what about air resistance? Yeah, it's going to slow down a little bit, so it's probably not going to be exactly 96 feet per second, but watermelons are pretty dense. So anyway, so this next problem has to do with hiking, and it mainly just illustrates sort of the relationship between the watermelon and the slope problem. You might be able to figure out that the slope problem is the watermelon problem. But let's take a look at this. I'm hiking up to Observation Point at Zion National Park. The hike is 3.75 miles long. The start of the hike is 4,345 feet above sea level, and the end of the hike is 6,572 feet above sea level. So you understand the situation is here we are. We're getting ready to hike. We go up this hike, and at the top, you have a rise and you have a run. So the run is 3.75 miles. The rise is, well, what is the rise? So I want to know, how steep is this trail? What's the slope of this trail? Slope is rise over run, isn't it? So let's figure out how steep that trail is. I guess I need to know the rise. So I'll give you a minute, see if you can figure out what your vertical difference is there. And let's see, I've got my randomizer still. Thomas, were you able to figure out how high you get, or like what the vertical difference is? And how did you figure that out? It's the difference, right? Yeah, so it's the difference of the top minus the bottom. Top minus bottom. So whenever you talk about slopes, slopes are just divided differences. It's the difference in the y divided by the difference in the x. And so that's all a slope is, rise over run. And so yeah, we've got our rise is 2227. And then the run is going to be, oh, that's a different set of units, isn't it? So if you ever have this situation, don't let it throw you. Just make sure you have the same units. We all know 5280 is the number of feet in a mile. Okay, maybe you didn't, but you could Google it. And so this is going to be 1,000 or 19,800 if you do 5,280 times 3.75. You should get that. So there it is. Let me do this on my calculator because I can't do this in my head. And we get 0.11. Whatever, 25. So that is the answer to part 1. So a slope, rise over run. You can imagine walking along a trail. Now, I don't know if you've ever walked on trails, but 0.11, that's moderate. It's not terribly steep. But something I didn't tell you is that at mile 2, the trail is 5,645 feet above sea level. And at mile 3, the trail is 6,520. So different sections of the trail are going to have different steepnesses, as you probably can get. Let's see if we can find the slope for that section of the trail. Rise over run again. I'll do the run for you. For this section of the trail, it's 1 mile across, and so that's going to be 5,280 feet. So all you have to do is tell me what the vertical change is. So we're Allie, is that right? Wait, Allie Farnsworth? Oh, that's you. You're Allie in here.
Yeah, I think that must have.
What are you really?
I go by either.
Which one do you prefer?
General is an easy for me.
Well, I can change this. So, yeah, let's see. Yeah, here we go. Can I change it? Yes, no, I can't change it. I'll change it later. So you tell me which one you prefer. Alexandra, Allie?
Alexander's fine.
Okay. Let's see. I'll deal with it. I'll deal with it later, I think. Can I not? Yeah, I'll figure it out. Alexandra. Okay, Alexandra, how high are we going? So we want to know the difference between that height and this height.
875.
Okay, 875, very nice. And so then we're just going to do this difference on our calculator, 280, and I've got 0.1657. So that section of the trail is a little bit steeper, a little bit more strenuous than I guess the average. This is an average slope. This also is an average slope. Both of these, by the way, are what we call secant lines. So a secant line, I'll draw this in just a minute. But this last one, if we start off 250 feet, it's completely flat. And then the elevation increases to 4,780. Let's do this. So this is 4,780. And we started out at 4,345. And this here is 250. And this here is half of a mile, which is 2640. So we're going to have to do a little bit of math here to figure out the slope of this section right there. So I know my markings are super messy. Hopefully you can interpret what I have there. So here I think it would probably be best to actually write this as a divided difference. So slope is equal to the rise. Notice the difference in the y values divided by the difference in the x values. So anyway, go ahead and do that, and then we'll see how you did, or how I did. Elena, were you able to do this one?
Oh, I was just waiting for you to send back out so I can see the numbers.
Oh, well, these are the only numbers you need.
Okay.
There, I could zoom back out a little bit. Yeah, my drawing is terrible of the situation. Yeah, I thought you were done. My apologies. All right, so maybe you could check, make sure I got it right. We'll do, I got a slope of 0.182. Anyone else get something like that? Doing the difference there? Okay. 182. So I know it's still like doesn't have a lot of meaning to you if you're not used to hiking or understand. That's pretty steep. So, you know, you're gonna feel it at the end of that. Anyway, so this illustrates the difference between a tangent and a secant. So let's just imagine I'm going to draw this hiker again. And in reality, a hiking trail is not a straight line. Well, it's not even straight horizontally, but anyway, you have something like this. So you start down here, you end up here. So when you're standing on the trail, like right here, you're like, hey, that's not very steep at all. Whereas if you're standing on the trail here, this is steep. So this is like easy. How about that? So what you're thinking about when you're standing on a trail about how steep it is you're thinking about the tangent. A tangent line is a line that is similar to a curve or looks like the curve when you zoom into the curve. So you've got this curve, this trail. These are tangents. Tangents. I'll draw another example of this in just a minute, but I just wanted to get this trail thing out of the way. So that's the tangent line. A tangent line is just like the tangent to a circle, touches the circle in one point. Tangent to a curve, touches the curve in one point, at least locally, if you zoom in far enough. That's what it looks like. On the other hand, a secant line, a secant line is what you get when you connect 2 points. So like this, from here to here. So that is a secant. We're going to do this again with another function, not this thing that we just did, something a little bit easier, hopefully, to imagine, or actually we can draw. So let me do this with this function, which I know you're looking at that saying that's not very easy to draw. Well, let me go ahead and draw it for you so that we can see what it looks like. In fact, I think what I'd like to do is I'd like to go back to, let's see, go back to my notability here just a sec. I'll paste it in here. There. So it's missing the function. This is y is equal to, let me see, where is the function? There it is. Y equals 4 minus the cube root of x. 9 and 1, yeah. Okay, so this function. Oh, I'm missing all of this stuff too. X equals 9.1. We'll just do those two for now. Okay, so what this is referring to is this, is you can imagine taking this graph. I can graph this. Let me go ahead and graph it for you. 4 minus the cube root of x looks something like this. This is the point 9, 1. Okay, so what we're trying to illustrate here is the difference between a tangent and a secant line. So let's start off with secant lines. So a secant line, you could connect 2 dots. So take that point there and take this point, 9.1, 9.1. I'll need to get the y value for that. And I can connect those 2 dots with a curve, or rather a straight line. There we go. And that is a secant line. So I guess I need to come up with the function value. So your next job is to plug on your calculator, take 4 minus the cube root of 9.1. Do that on your calculator, and we'll see where we are. Zach, it looks like you got it.
I think so.
All right, what you got?
I got 1.91.
That's 4 minus the cube root of 9.1.
Yeah. Let me see.
Oh, crud. Ah, I see. I blew it. I need to change this problem. Sorry. I'll blame it on being too early in the morning. Let's do it this way. Change this to 8 and this to 2. Sorry about this. Okay. So if you were looking at that saying, wait, 9, 1, that's not on that graph. You're right. Not on the graph. I did the square root instead of the cube root when I was setting this up. Okay, let's start fresh. Let's just go to the bottom and start fresh. Okay, so we're going to start with this. Y is equal to 4 minus the cube root of x. And I'm going to start at the point 8, 2. So let's double check. If you plug, let's call that f of x. F of 8 is 4 minus the cube root of 8, which is equal to 4 minus 2, which is 2. Okay, double check. So that's my poor mental arithmetic. So let's start fresh with this one. So you have this curve. Here's the point 8, 2. And I'm going to just go a little bit over to the point 8.1. And so now not 8, I want 8.1. So sorry about that, but thank you for helping me to keep myself straight. So we're going to do basically the same question, only I'm going to ask the question, what happens if we go over from 8 instead of 9? So anyway, plug 8.1 into this function here. Take a minute, and I'll pick another. Thank you, Zachary, by the way, for keeping me honest here. So when you get a chance, Allison, were you able to plug 8.1 into this function? Okay, excellent. Okay, so now what we're going to do is we're going to compute the slope of the secant line connecting those two. So this thing, the slope is rise over run. So 2 minus 1.991 over run, that's going to be 8 minus 8.1. So I know this is a little tedious, but you can do this. This is going to move this over. All right, let's see how we did. Let's see, randomize again. You're not here. Thomas is here, though. Thomas, were you able to get this slope?
Negative 0.0.
Okay, very good. Negative 0.083. So that's the approximate slope of this thing. Just see, does that make sense? Yeah. Sure. All right, now we're going to do the same thing, but we're going to bring this point a little bit closer. So a limit is what you get when you take, like, let's see, can I do this without disrupting this too much? Hold on a minute. Take that point. Oh no, the whole thing's going to move. Sorry, I should have done it like this. Oh, I could do this. Nope. That's what I want. Okay, so this dot. If we move this closer and closer, you could imagine that this secant line is going to get closer and closer to what we would consider the tangent line. Tangent line would be something like this, where it just touches the curve just at that point. So if you imagine, oh, come on. I keep clicking the wrong thing on my iPad. So if you imagine moving this closer, then your secant line will get closer to that green line. So let's do this again, but use, let's do the point 8.01. So let's use that point instead of 8.1. So I need to know what f of 8.01 is, and then we'll plug that into our little slope formula. So take a minute, and first of all, we need the function value at 8.01. I see that I only have 4 minutes now. And let's see. Okay. All right. Let's see this. All right, so Kelsey, did you get a function value for this?
I can't figure out how to do the cube root on my calculator.
Oh, interesting.
I have the
Okay.
wrong calculator with me.
Okay, so no, that calculator has a cube root. The way you do it is you do, so you would punch in 8.01 and then use that key there. And then I guess you'd have to do parentheses 1/3. There may be a easier way to do this, but that'll do the cube root on that calculator. Yeah, there's
I don't think so.
there may be a math bot, but anyway, this will do it as well.
Okay, 1.99 or 1.999. So it is 2.
What, the next one is a 2?
It's 3 nines in the hundredths place,
And then what's after that?
and then 1.
Then a 1? Okay. All right, we'll go with that. All right, excellent. So then we're going to do the slope is 2 minus 1.9991 over 8 minus 8.01. And this should be a little bit closer to the true slope. So let's see if I can do this. 1.9991 divided by 0.01. And I got 0.09, negative 0.09. So this negative 0.083, I feel like it shouldn't be, it should be actually smaller. Well, there must be some rounding, some issues with rounding maybe that we're having here. But be that as it may, we do need to get on to the final thing, which is we never got to the area. So we're just going to have to drop that off. Homework preview. So let's take a quick peek at the homework so that you know what to do for next time. So here's another thing that I'm getting used to the new system is that this stuff, if anyone actually attempts a homework set before I have a chance to edit it, I can't edit it anymore. So my apologies for that. Although I could just clear, you know what, that's what I'll do. Let me just do this really quick. So let's see, where is the editing? Hold on a sec. Questions. Yeah, so apparently someone has, let's clear them. Someone's tried this assignment. This is the one due tomorrow. Okay, now I can delete. That's what I wanted to do. I wanted to delete this last one or the last two. How can I see these? It's so hard to see up here on the screen. Just a sec. And then we'll do a preview. Give me a sec. We're going to delete this one and this one. Yeah, so I'm just deleting 2 of the questions because we didn't get to them. Remove. Okay, now I think we're good. Can I save this? I'm done. Okay, now let me show this to you. So sorry about that. And teacher preview. Okay, here we go. Okay, so here's what you're going to be looking at. So you have several problems that ask about, like, what is the slope? The slope, hopefully you can figure that one out, some basic definitions. Slope of a secant line estimates the slope of the function at the point. So hopefully you can get that. And if you don't, remember you get extra tries. So these are sort of conceptual problems. Oh, this one, t approach is letting t approach an expression is a limit. Okay, so that one's fine. Seems like there's one more that I should have deleted. Okay, some slopes, which you can do. Slope of a secant line. Oh, here we go. Just to make sure that you don't lose your mind here. So once you have the slope, you can use that slope to come up with the equation of the line by using point slope form. Hopefully you can do that. That's not too bad. And then this is the one. I got to delete number 6. Give me a sec. I'll delete that. Don't try it until I've deleted that one and that one. So, in fact, I'll just delete a whole bunch of them here. So I'll delete them, and then you'll be okay because it'll be a nice short assignment. All right, so thanks for coming, and hopefully we'll get the kinks worked out of dealing with the homework. So my apologies with the homework issues, but we'll get it worked out. Remove. There we go. Done. Phew.
See you tomorrow morning.
All right, we'll see you in the morning. Take care.